All right, so we've talked about how to calculate the pH of weak acids. We've talked about how to do it with weak bases. We've talked about polyprotics, all sorts of things. What we're going to talk about next is something that's maybe not quite as obvious that we need to talk about. So here's a question for you. What is the pH of a solution with 0.1 molar F- concentration? You're like, well, Professor Clements, there's no acid there, there's no base there, so I mean, isn't it just kind of a neutral solution? Isn't it kind of like water? And the answer is no. It turns out if you had a solution of sodium chloride, then that has a pretty neutral pH. Not much is happening. But if we have a solution that's got F- in it, it's not going to have a neutral pH. And why is that? Well, if you remember, HF is a weak acid, right? Which means as it dissociates, we get a very small amount of this stuff and mostly this stuff. Which means if you have a solution that has a bunch of F- in it and maybe some H+, would it rather be H+ and F-, or would it rather be HF? And with very small K value, we're saying, hey, that's probably going to be something that prefers to be HF. And so what's going to happen is if you just have a solution with a bunch of F- in it, it's going to find ways to react and find H+. Now, there's not much H+ in solution here, right? It's about 10 to the minus 7th molar, so it's probably not going to be going out and actually finding H+ directly. More likely, what it's going to be doing is finding water, because there's a whole lot of water in this solution. And if it finds the water, it's going to be able to react to make its HF and leave behind my OH-. Now, obvious on all of these, I should be putting my subscripts for my phases, because that's just good practice. So let's go ahead and add those back in. So that's what's going to be happening in a solution. The F-, because HF is such a weak acid, it would rather be HF than F-, and so it's going to go and find places to find some H+. So it's actually going to come up to water and say, hey, can I have some of your H+? And water, sure, I'm happy to do that. Because remember, water's amphoteric, doesn't mind if it's an acid, doesn't mind if it's a base. So what we're going to do then is we're going to calculate what would be the pH of this solution, given that we know it's producing OH-. So we know just kind of off the top of our head the pH should be basic. It should be above 7, but let's go ahead and calculate it. So we're going to say we have a solution that's 0.10 molar F-. And we're going to calculate that pH. Well, it turns out it's just a straight ice table. F- plus H2O goes to HF plus OH. And that's great. We ICE this, CE. We have 0.10 molar. We don't care about water because it's a liquid. HF, we don't have any to begin with. OH-, we have the contribution from water. It's not 0, but it's probably close enough to 0 that we don't have to worry about it. And we go ahead and do our ice table, and guess what this ice table is going to look like? Yeah, every single other ice table we've done in this chapter so far. X, X, minus X, 0.10 minus X, X, X. And then we have K. K is going to be HF OH over F-. Now you look at that and you think, well, that doesn't look like a Ka. I'm not going to put a subscript A here because that really doesn't look like Ka, because Ka is HA breaks apart into H+ and A-. I don't have that. What did we have that breaks apart into OH-, right? We had our generic base equation. Now, this one's a little bit different because if you remember, our generic base equation was B and BH+. Now, like, there's no plus sign here, but the point of B is not that B is neutral. The point of B to BH+ is that it gained 1 in charge. And going from F- to HF, we gained 1 in charge, and we gained a hydrogen, which is the requirements of our generic base equation. So what we actually have here is a Kb. So I'm just going to go walk over to my tables of data, and I'm going to try to look up the Kb for F-, and hey, there. There's no Kb for F-. In fact, the Kb table is pretty darn small. There's not many Kb's at all. Where are we going to find the Kb for this guy if it's not in the table? Well, it turns out what you're going to do is you're going to look up the Ka, but I need the Kb. It turns out, and I'm not going to go over the details of this, it's a pretty easy derivation, but I'm just going to give you the answer, that Ka times Kb is Kw. So there's a relationship between Ka and Kb. If you know the Ka for something, you know the Kb for it. If you know the Kb for something, you also know the Ka for the same thing. So if I can look up the Ka for HF, which is Ka equals 3.5 times 10 to the minus 4th, then I can just go ahead and calculate the Kb is going to be Kw over Ka, or 1 times 10 to the minus 14th over 3.5 times 10 to the minus 4th. If you do that calculation in your calculator, you should get a 2.9 times 10 to the minus 11th. And so we can set that up here as 2.9 times 10 to the minus 11th and put in our values, x squared over 0.10 minus x. Great plot time to use the small x assumption. I mean, we've got 10 orders of magnitude difference. I think that's OK. So coming back to our solution, we're going to use the small x assumption. And now we've got that 2.9 times 10 to the minus 11th is equal to x squared over 0.10. We go ahead and solve that to find that x is equal to 1.7 times 10 to the minus 6. Now remember, x, if we go back up to our table here, x is not H plus concentration. It's so tempting. We're so used to doing acids. It's not H plus concentration, it's OH minus concentration. And so this is equal to my OH minus concentration, which means I can go ahead and find the POH by taking the negative log of 1.7 times 10 to the minus 6. I get 5.76, and then the pH is just going to be 14 minus 5.76 is 8.23. 2 sig figs, 2 digits after the decimal. Right, 2 sig figs in our K values, and 2 sig figs after 2 digits after the decimal in our pH. So 8.23, it is slightly basic, exactly what we'd expect. So it's interesting. So even sometimes when there's not an obvious acid or an obvious base around, we can change the pH of solutions, which is kind of neat. So what did we find? We found that the anion of a weak acid, our HF, when it dissociated, it produced H plus and F minus. This is a weak acid. And what we found is that F minus on its own is a weak base. Right? If we put F minus into solution, we just found that the pH was 8.23 on a 0.1 molar F minus solution. So that's basically acting as a weak base. So that's an interesting thing. And in fact, there's words for this stuff. HF is our weak acid, and it produces F minus, which is the conjugate weak base. Now, what does conjugate mean? It took me a long time when I first learned chemistry to figure out what conjugate meant. And it turns out it's actually really, really easy. Acids and bases are on the left-hand side of your chemical reaction. Conjugates are on the right-hand side of your chemical reaction. It really is that simple. It's how you write it. Acids and bases are always on the left-hand side. Conjugate acids and conjugate bases are always on the right-hand side. So I'm going to write this out a little more completely here and say HF aqueous plus water. So I'm going to do the one with a hydronium ion here. And we decided that this guy is a weak acid. This is a weak conjugate base. Let me scroll that up for you. That's a weak conjugate base over there. What about H2O? Well, H2O is acting as a proton acceptor. That is a base in the Bronsted-Lowry definition. Then what happens? Well, on the right-hand side, it now has that proton. So what does that make it? It makes it an acid. And we're not going to talk about whether water is a strong base or a strong acid, weak base. Weak acid is weak. I mean, we know that it's not like raring to give up its H. It's not raring to take an H. It'll just kind of do whatever. But do we call it an acid on the right-hand side? No, we don't call it an acid. We call it a conjugate acid. Why? Because it appears on the right side. That's it. Just because it appears on the right-hand side. That's the only reason we call it the conjugate. Okay? It's paired always with a base. You don't have a conjugate acid without having a base. But when you write a balanced chemical reaction, you use conjugates for things on the right, product side, acid base for things on the left. I'm going to show you that even a little more clearly now. Let's just take this same equation and just write it backwards. F minus plus H3O plus goes to HF plus H2O, something like that. What do we have? Well, turns out we know that F minus is a weak base, which means after it accepts that proton, it must be a, weak conjugate acid. H3O plus is going to be giving away that proton so that HF can form, so that makes it an acid. And there's always a base and an acid. There's never two acids in these kind of balanced chemical reactions where you're doing acid-base chemistry. And that must make this a conjugate base. So you can never just say, oh, F minus is a conjugate base. Well, it's not. In this case, it's a regular base. It's a weak base because I wrote it as a reactant. So there's nothing inherent about a given chemical that it is a acid or it is a conjugate acid or it is a base or it is a conjugate base. It depends entirely on the context of the balanced chemical reaction that you're writing it for. If you write it and it's on the right-hand side, you call it a conjugate. If you write it, it's on the left-hand side, the reactant side, you just call it an acid or a base. Okay, so let's explore this a little bit more. How do I identify conjugate acids and conjugate bases? HCl, what do we know about that? We know it's an acid, again, if it's written on the left-hand side of an equation, H2O. In fact, what do we know about HCl? We actually know specifically it's a strong acid, and so we generally write this one reaction arrow there, and we're going to say that forms H3O plus and Cl minus. All right, so if HCl is a strong acid, it's giving away its H plus, H2O is accepting it, that makes H2O a base. What does that make H3O plus? Well, hopefully you said, well, it's a conjugate because it's on the right-hand side. So I'm going to write that first, conjugate. And then what you want to think of is, if something an acid is something a base, is what's it going to do with the proton? So you've got a little proton here, and whoever has that proton is the acid. So right now, this hand has the proton, and so it is the acid. This hand doesn't have the proton. It would like to accept the proton, and so it's the base. Ding, 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 ding. Reaction happens. Now, this is the base because it lost the proton, and this is the acid because it has the proton. And we go ding, 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 reaction, and now this guy's the acid, this guy's the base. So you just follow the proton. Follow the proton. Whoever's got the proton is the acid. Whoever doesn't have the proton is the base. And that's as simple as that. It gets a little more complicated when you have polyprotics, because then what do you mean who has the proton? Because I lost one proton already, but I got another one. Does that mean I lost my proton? I have the proton. I need the proton. And we'll talk about that in just a moment. So let's go back to this one. HCl, H2O, H3O plus. What do we have? Strong acid for HCl, base for water, conjugate acid, right? If you follow that hydrogen, we know that H3O plus is going to be an acid. And then what about Cl minus? Cl minus, well, if HCl was the acid, it always occurs in pairs. This must be the conjugate base. Why? Because it no longer has the hydrogen, right? HCl gave away its hydrogen. It's like, oh, I'm just Cl now. I'm a base. Okay. Now, what do we know about that? Is Cl a good base or is it a bad base? Right? Is it a good base or a bad base? What do you mean by a good base or a bad base? Well, what does a base do? A base will accept protons. Is this a great proton acceptor? If I have Cl sitting there and saying, hey, 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 da, 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 and a proton comes by, is he going to say, oh, let me have that? Well, what do you know? HCl is a strong acid. So even if he said, hey, let me have that, he's going to go, I don't want that anymore. And he's going to get rid of it. That makes him a very bad base. He's not very good at being a base. Even if someone gives him a proton, he's like, I don't want it. And he spits it right back out. So not only that, we have a conjugate weak base. In fact, a very, very weak base. And so, these weak and strongs, remember there's a range of them. There's only a few strong ones, right? So you're not going to label anything as strong unless it's one of the strong ones that you talked about. So everything else is weak, and it's just a range of weak. Cl- is an extremely weak base. Very, very bad at being a base. But it's a conjugate here because I wrote it on the right-hand side. And that's all there is to it. So how about if somebody just handed you a chemical and said, hey, what is the conjugate base of H2CO3? You're like, I don't know. I need a reaction, right? I need something on a product side. I need something on a reactant side. Okay, so let's write a reaction. Okay, if we're going to look for the conjugate base of H2CO3, we're going to start with H2CO3 on the left-hand side. We know we're doing acid-base chemistry, right? And so what's going to happen? H2CO3 is either going to lose a proton acting as an acid, or it's going to gain a proton acting as a base. What's it going to do? Well, you remember, right, when we write those H's in front, that's usually indicator of an acid, so we could probably guess that this is going to be an acid, but the language in the problem actually makes it extremely clear. It says, hey, what is the conjugate base, right? In order for something to have a conjugate base over here, that means it needs to have an acid on the other side. So this guy's got to be acting like an acid. If he's acting like an acid, he is giving away an H+, and we're going to have H3O+, plus whatever that conjugate base is there. So we're able to fill in kind of this reaction here. But now what happens? H2CO3 loses a proton. It becomes HCO3-, and that's our conjugate base. So the conjugate base of H2CO3 is HCO3-. So you can do all that, and that's actually really important to understand that that's where it all comes from. But there's also a shorthand, right? When I'm asking for the conjugate base, right, that means it's acting as an acid, because it has to, and it's going to lose an H+. And so when going from H2CO3, I have H1, and I decrease my charge by 1 from a charge of 0 to a charge of -1. So right, you're giving away H+, you're changing the charge from 0 to -1 there. How about the conjugate acid of HPO4-2-? HPO4-2-, you know what the conjugate acid? Well, HPO4, you've got that H in front. Does that mean it's going to act like an acid? Well, you have to look at the context of what you're being asked for. The conjugate acid of HPO4, let's write out the whole thing and think about it, and then we're going to go back to the tricky, easier version. HPO4-2-, right, we're going to react that with water. And let's see, in order to have a conjugate acid over here, right, that means this must be a base, right? I've got to have a base over there because you always have conjugate acids and conjugate bases together. Okay, so the base, well, what's the base going to be? Well, it's not going to be water. It's probably going to be OH-, probably, right? And which means that the conjugate acid has got to be this thing, which means this thing has got to act as a base. This one's got to act as an acid. It's kind of like a Sudoku puzzle, right? Once you know this one, you know that there's always a certain number of these other ones, and you can start to fill in the blanks there. So we know that water's acting as an acid. If that water's acting as an acid, it's giving away H+. So that means that my base, HPO4-2-, is taking that. And so it's going to have H2PO4 with a -1 charge. Okay? So again, filling in those blanks, but we can also kind of shorthand, right? In order to have a conjugate acid, that means on the reactant side, it must be acting as a base. A base accepts hydrogen. And so a conjugate acid is going to accept an extra hydrogen. The hydrogen has a plus charge, so I'm going to change my charge as well from a -2 to a -1. I could also have asked the question, what is the conjugate base of HPO42-? I could have asked that question. In that case, since we're talking about the conjugate base, it means it needed to act like an acid. It acts like an acid by giving away H+, right? And that thing's more basic. The thing, when you're asking for the conjugate base, right, that's a product, and you're going to get something that's more basic. So that's great. That's exactly what we would expect. Okay. So we should be able to identify conjugate acids, conjugate bases just by being asked to. We should be able to write these balanced reactions if we are asked to as well. Remembering that when you have a strong acid, you end up with a very weak conjugate base. And when you have a weak acid or a weak base, you end up also with a weak conjugate. And the strength depends on the strength of your thing you started with. All right. I think that last part was not said as clearly as possible, but hopefully you figured it out. Question, where do we get F-? I said, hey, when we were talking about this, let's put together a beaker of F-. But we can't just do that. We can't just put together something with a negative charge, right? Nature always loves balance. In order for that F to take that extra electron, he had to take an electron from somebody. Where did he take the electron from? So generally, where we get things like fluoride ion is from a salt of the fluoride ion, sodium fluoride, calcium fluoride, lithium fluoride, one of the salts, right? A metal combined with a non-metal in an ionic compound. And so what we actually would put into here is sodium fluoride, and we'd have sodium and fluorine floating around. Now here's the question, does sodium do anything? Does sodium react in there and change our pH? Is there anything we know where Na+ reacts with water to form maybe NaOH plus H+? So it's going to take the OH from the water. And maybe that's not unreasonable to think about, but what do we know about sodium hydroxide? It is a strong base, which means it's an extremely weak acid, and so it's not going to do this. As soon as it does this, it's going to undo it and go, oh, I just want to be sodium. I just want to be by myself. Can you stop bothering me? Right, so what's sodium going to do in there? Absolutely nothing. So sodium is not going to affect the pH. F- we know is going to be basic. It's a weak base. And so combining those things, we can say overall, we know this solution is going to be basic. And so now we can actually look at a salt and say, hey, a salt solution is basic if one or both of the things in there are acting as a base. A salt solution is acidic if one or both are acting as acidic. And we'll get later on to what happens if we have both or what happens if we're not sure. All right, but for now, well, let's look at ones that are a little more obvious. So let's take another example. NH4Cl. And this is also where knowing those solubility rules that you learned in first semester general chemistry is really useful. To know that chloride salts are generally soluble, to know that ammonium salts are always soluble in water, means that this will dissociate into NH4 and Cl- in solution. And because it's NH4 plus and Cl- in solution, we can consider these entirely separate of one another. We don't have to think, what does NH4Cl do in solution? And we shouldn't think that. We should think, when we put NH4 and Cl in solution, it dissociates into NH4 and Cl-, and those now act and behave entirely independent of each other. NH4 plus is certainly not on our strong acids or our strong base lists, okay? And it's not the conjugate of a strong acid or a strong base, right? NH3 is not on our strong acid, strong base. So we can guess that this is some sort of weak, what do you think? Is it an acid or is it a base? Generally, just, if you're looking at something and it's got a plus sign, you probably looking at an acid, okay, especially if you've got lots of hydrogens around. But let's think about what it is. What do we know? We know NH3 and we know NH4. And so if we're looking at that little hydrogen, right, NH4 plus, he's got that extra little hydrogen there, which means he can also give that hydrogen back and give it away, right? NH4 plus can give off a hydrogen to form NH3 and H plus. So this is going to be a weak acid, and it's going to make our solution slightly acidic. What about the chloride ion? What do we know about the chloride ion? Well, the chloride is the conjugate of HCl. How good is chloride at accepting an H? It's awful, right? It's absolutely awful. It's not going to accept an H, right? Because if it does, it forms HCl. And what is HCl? HCl is a strong acid, so it's going to spit that H right back out and do nothing. Now, that's not the only thing, right? There's actually 4 different things that an ion could do in solution. So Cl, we have to actually think about 4 different things. 1, 2, 3, 4. 1, something could give away H plus. It could take H plus. It could give away OH minus, or it could take OH minus. And so if we're considering an ion and we aren't sure what to do with it, we actually have to go through all 4 of those. Some of them you'll start to recognize over time. You're like, okay, chloride doesn't do anything, sodium doesn't do anything. But for other ones where you're not sure, go through this list of 4 things. Is it going to give away H plus? No, it has no H plus to give away. Is it going to take H plus? Okay, what would happen if it did? It would form HCl. But what do we know? HCl is a strong acid, and so it just goes and spits it right back out. Nothing happens, essentially. Is it going to give away OH? No. Is it going to take OH? Well, you think about it. Is something negatively charged likely to attract negatively charged OH minus? And the answer is no. So it's very unlikely to take OH. Now, there's exceptions when you get hydrogen, right? We're going to see sometimes where maybe something has charge and takes the hydrogen, but for the most part, opposite charges. Right? Opposite charges are the things that attract each other. In fact, I just realized I'm not going to be doing things where the same charges attract each other. I was thinking about something else. So opposite charges, right? A plus and a minus attract each other. A minus and a minus repel each other. They're not going to approach each other in solution, right? So we just eliminated that one. We eliminated that one. You eliminated that one. You eliminated that one. If you have eliminated all 4 of them as possibilities, that means this guy does nothing. Okay? And it's not going to affect the pH of solution. Not to say there's no chemistry with chloride. There's no pH chemistry with chloride. And so we have ammonium chloride. Ammonium is going to act as a weak acid. Chloride is going to do nothing. So overall, ammonium chloride should make a slightly acidic solution from the weak acid ammonium. Let's do another example. Let's go ahead and do an example where we've got some, let's keep it simple. I had another example, but I'm going to change it up. And we've got some 8K NO2, some potassium nitrite. Well, let's look for our solubility rules first. If it doesn't dissolve in solution, not much is going to happen. Potassium, always soluble. Good. Okay, so we know that when we put this into solution, it's going to form K plus and NO2 minus. And we can now consider those 2 entirely separate from potassium nitrite. So if someone asks you, what does potassium nitrite do in solution? Does it make an acidic or basic solution? You don't have to answer that question directly. You answer that question by saying, well, I know that potassium nitrite is soluble in water and it's going to break apart into these ions. So let me explore what each individual ion is going to do. So let's look at K plus. What might it do? Let's look at our 4 different things. Is it going to give away H plus? No. Is it going to take H plus? No, right? Same charges are going to repel each other in solution. Is it going to give away OH minus? Doesn't have it. Is it going to take OH? Well, that's a thought, right? We say, hey, K plus takes that and makes KOH, but what do we know? We know that KOH, potassium hydroxide, is a strong base, so even if it made it, it would immediately fall apart again, ding, and spit that OH right back out, and we'd just get our K plus back, and nothing would happen, okay? So the K does nothing. Right? It's not going to affect the pH of solution. How about NO2 minus. And again, if you're unsure, go through the 4 things. Is it going to give away H plus? It doesn't have H plus to give away. Is it going to take H plus? That's a nice opposite charges like this, H plus to form HNO2. That sounds something reasonable, right? We know that HNO2 is a weak acid. How do we know that? Because it's not one of the strong acids we memorized. And so if it's a weak acid, it would prefer to be HNO2 rather than NO2 and H+. So that's a definite possibility. Let's do that other one there, other two, just to see. Is it going to give away OH? No, because it doesn't have OH to give away. Is it going to take OH? No, because that's the same charges. They're going to repel each other in solution. So this is our only possibility, and that's a really good possibility because we know HNO2 is a weak acid, and it would prefer to be HNO2. So NO2 is likely to react with H+, taking it out of solution. Now another way to think of this that's sometimes a little bit easier for people is really what it's going to react with is the water in solution. And it's going to take away an H+ from the water, leaving behind OH minus. So for some people that's a little bit easier to think of. Instead of saying, oh, it's going to extract H+ from solution, which is like, well, what does that leave behind? And the answer is less H+. Less H+ means more OH minus. You can also think about it reacting with water, taking the H from water, and actually spitting out some OH minus from that water. In either case, what it's going to do is it's going to leave the solution slightly basic. Okay? So overall, a solution of potassium nitrite is going to be basic because of the nitrite ion, the potassium ions, doing nothing. All right. Now, what's another way of getting an acidic solution? Another way of getting an acidic solution is with highly charged, cations. Now, why would a highly charged cation give you an acidic solution? That seems a little bit strange. So let's go ahead and use an example. We're going to use an example of iron 3 nitrate. What do we know about our solubility rules? We know our solubility rules tell us that this is going to break apart into iron 3+ aqueous and 3 nitrate ions, because nitrates are always soluble. So we know that is going to be the case. When we think about nitrate, right, it's the conjugate base of nitric acid, which is a strong acid. So chances are it's not going to do anything. It's not going to give away H+. It's not going to give away OH because it doesn't have it. It's not going to take OH minus because it's the same charge. So the only other thing it might do is take H+. But if it took H+, it would form HNO3, spit it right back out, and you just get the NO3 and nothing would happen. So we know this is going to have no effect on our pH. Okay? But what about the iron? What about the iron? What's it going to do? And you look at that and you're like, well, it's iron. We haven't really talked about chemistry of iron at all. So let's talk about some chemistry that might happen with this iron. It turns out if you have a highly charged cation, what is highly charged cations? Highly charged cations have a 2 or greater charge, and they're usually in the transition metals. Okay, so a 2 or greater charge in transition metals. Or aluminum. Aluminum's not in the transition metals, but it also does this. If it has a 2 or greater charge in the transition metals, one of the things it can do is react with water. And in fact, it's going to react with several waters, usually 6, not always 6. I don't care. Like, there's actually rules about which ones, and I don't care. As long as you understand this concept, just say 6 waters, and we're fine. Okay, so we're going to say that it's going to react and make this complex, which also has a 3+ charge, right? Because water is neutral. That doesn't do anything for me, Professor Clemens. I don't really see what's going on there. But let's look at the structure of that one, right? It's going to be octahedral. It's going to have 6 things, right? It's going to have water there, water here, water here, water there, water there. So let's just look at one of the waters. Okay. Remember, this Fe this iron has a +3 charge. It's highly positively charged from our Lewis structures and studying dipoles, we know that that oxygen there on the water is negatively charged. So these two are very highly attracted to each other. That Fe3 plus, that iron 3 plus, is pulling away electrons from that oxygen because they're oppositely charged, essentially. And as it pulls away electrons from that oxygen, it's also, that oxygen is going to pull even more electrons away from that hydrogen. There's these chain effects, right? If I pull on this rope, it pulls on this part of the rope, which pulls on that part of the rope. So as I pull electron density away from oxygen, it's also going to pull electron density away from hydrogen, because there's going to be a little more charge that oxygen would like to have that it just got taken away by the iron. And so this guy is going to even be more positive than it normally would be. And it turns out that if you have a highly charged, 2 or greater charge in the transition metals, if you have a highly charged cation, then this can get, what do I want to say? The hydrogen can get positively charged enough that it actually just pops off into solution, pop, as H+. And it actually makes the solution more acidic. So what gets left behind? Well, then we get H, oops, this is not a plus, this is an arrow, and we get Fe H2O 5. So 5 of the waters do absolutely nothing. One of the waters lost its charge, leaving just behind OH. Yeah, 2 plus. We lost an H plus, so our charge changes, and we have H plus. So we left behind, we took off one of those hydrogens, it floated off into the solution, making the solution slightly acidic, leaving behind the iron with still 5 waters intact around it, and then 1 hydroxide looking thing. So small, highly charged cations can give you an acidic solution. Now, what if I were to tell you something about, let's say, strontium, right? Strontium nitrate, Sr. Is that going to do anything? And you're like, oh, look, I've got strontium. It's going to break apart. All my nitrates are soluble. I've got strontium 2 plus. That's a metal, and it's got a +2 charge. Let me go ahead and do this thing that you just did, Professor Clements. But notice that strontium is not a transition metal. So you don't want to do it to strontium. Strontium's not going to do that. Strontium, you're going to do the 4-thing test, right? It's going to take OH, give OH, take H+, give H+, and you're going to find that it does nothing, because the only thing it might do is take OH-, but it's a strong base. Strontium hydroxide is a strong base, so even if it took OH, it's just going to give it away again. So not much is going to happen. So you're really looking at the transition metals, or aluminum, and highly charged. Okay, so here are some for you to try. So we're going to do a few of these, and then we're done with this section finally. I know this was a longer video than normal. So a solution of 0.150 molar lithium carbonate is, what'd you come up with? Hopefully you said, hey, look, all lithium salts are soluble. I'm going to have lithium. I'm going to have carbonate. I'm going to figure out what happens to lithium. And you'll find nothing, right? It's not going to give away H+. It's not going to give away OH. It's not going to take H+, because it's similarly charged. The only thing it might do is take OH. Lithium hydroxide we know is a strong base, so even if it took OH, it would spit it right back out and nothing would happen. So this one's going to have no effect. Carbonate, not going to give away H+, not going to give away OH, not going to take OH. The only thing it might do is take H+, and let's see if that seems reasonable. H+ and CO3 2- is going to make HCO3. That seems reasonable, and it does do that, in fact. And because we know that carbonic acid is a weak acid, we know it would rather be H2CO3, right? It would rather try to get to that end if it can. So if we are taking H+ from solution, right, or you could write this as reacting with water producing hydroxide, we know that this is going to be basic. A solution of 1.45 molar potassium nitrate is ignore those numbers. We're not trying to actually calculate it here. Those numbers are just there to confuse you. Okay, They're not there to confuse you. I mean, people measure the molarity of these things. They might tell you these numbers, right? Your job in the world is not going to be to find information. Information is out there. Your job in the world is to figure out what information is important and what to do with it. So potassium nitrate, KNO3. What is potassium going to do, and what is nitrate going to do? How did we know that? Because we know that all potassium salts are soluble, all nitrate salts are soluble, so we know it's going to break apart into those ions in solution, and we're all good. Potassium, we've explored that already. Nothing's going to happen. Nitrate, we've explored that already. Nothing's going to happen. And so if nothing's going to happen and nothing's going to happen, we're going to have a neutral solution. A solution of iron 3 chloride. I forgot that I had this example. Hopefully you can figure out this one pretty well. A solution of iron 3 chloride is, did you come up with acidic? Fe3 plus 6 waters makes FeH2O. 6 makes FeH2O. 5OH plus H plus, making the solution slightly acidic. Very exact same example. I forgot that I used iron as my example later on. Okay, last thing, pH of salts of polyprotics. What about if we have NaHCO3? Like, okay, let's figure it out. Or if we had NaH2PO3. Right? Look at each one of these. HCO3 has a minus charge. H2PO3 has a minus charge. Okay? But we know from experience that HCO3 can fall apart to form H plus CO3 2 minus. We've seen examples of that. But is it also not inconceivable that it would take H plus, reacting with water, and form H2CO3 and OH minus? So we've got one path where it looks like it's going to be acidic, and one path where it looks like it's going to be basic. Let me actually put the water explicitly in this one. So H2PO3 could react with water and form H3O plus HPO3 2 minus, giving away an H plus, or it could form H3PO3 and hydroxide. So again, we have two different pathways, one of which looks acidic and one of which looks basic. And again, hopefully we got to knowing these ions are here by knowing our solubility rules, saying sodium is always soluble, so we're going to get sodium and we're going to get the bicarbonate ion. So hopefully you got that one, even though I didn't say it explicitly. So how do we know? How do we know which of these paths is going to dominate? Well, how do we know when we've got multiple equilibria, right? Because these are actually all equilibrium. How do we know if we have multiple equilibrium, which one's going to dominate? And we did that when we talked about mixtures of acids. We said, hey, let's just look at the different K values. Now, how do we look at the different K values for this? Okay? When we go to a table, let's just do it for this second one here. When we go to a table and we look up H3PO3, it's going to have a table of Ka1, Ka2, and Ka3. Okay? And so let me figure out what values I've got here. Ka1 is 5 times 10 to the minus 2. Ka2 is 2 times 10 to the minus 7. And I actually forgot to write down Ka3, but it's some smaller number. I think it's like 10 to the minus 11th or something like that. So what do we do? Well, what do we have? We have one that looks like an acid and one that certainly doesn't look like an acid. Right here, we've got HCO3 and H plus. So that kind of looks like an acid, right? But here, we've got this OH minus, and that doesn't look like an acid. So if we're going to look up, maybe we need to look up a KB, but we can't look up KBs. So how do we figure out what's going on? So hopefully you remember that the Ka1 is when you lose your first proton, the Ka2 is when you lose your second proton, the Ka3 is when you lose your third proton. So we have to decide here, what are we losing? Our primary one is H2CO3. That's our carbonic acid. So we lose our first proton, we get HCO3. We lose our second proton, and we get CO3 2-. So this reaction is actually Ka2, and that's going to be 2 times 10 to the minus 7. Okay, so that is for this reaction. What about that second reaction? And this is where it gets a little bit confusing for a lot of people, because you're like, well, I don't know which K to use. This looks like a Kb to me, right? I've got a something taking on water. Oops, I wrote that in the wrong section, didn't I? Okay, so this one is Ka2. My apologies. Which is 2 times 10 to the minus 7. Okay, so there we go. That makes a little more sense. Okay, so how do we know which K to use? We're starting with H2PO3. So do I find Kb2, which is going to be Kw over Ka2? Is that how it works? And the answer is you have to think about it properly. Okay? When you are thinking about turning a Ka into a Kb, what I always recommend is don't just look at a single species. Look at the equilibrium that you're talking about. And what I'm talking about here is an equilibrium between H2PO3 and H3PO3. Okay? And you're going to look at that equilibrium and find what the first possible step in there. H2PO3 to H3PO3, right? H3PO3 here is my parent, right? That's the actual acid, phosphorus acid. And then I'm talking about an equilibrium with that with H2PO3. So this reaction, that left-hand reaction, going backwards, is actually Ka1, right? I'm going from 3 to 2. That's the loss of my first proton. So it turns out the forward reaction is Kb1. And if you look just at the H2PO3, you might get confused. Like, is this number 2? Is this number 1? But if you look at the equilibrium and always think about what acid process is going on here. The acid process would be going backwards, H3 to H2. That's Ka1. That means the other way around is the base process. 2 to 3 is Kb1. It gets a little confusing, but I hope that you can kind of figure that out. Okay? But always when you're trying to figure out which Kb to use, or even which Ka to use, look at the equilibrium. Look at both species present. Don't just look at one species. If you look at one species, you can convince yourself either way. But when you look at both species, it's usually a little clearer. So we're going to try to find Kb1, which is going to be 10 to the minus 14th, Kw over Ka1, which was 5 times 10 to the minus 2. And so we're going to get 2 times 10 to the minus 13th as my Kb1. I'm going to scroll way back over here and write Kb1 over here is 2 times 10 to the minus 13th. So we've got 2 times 10 to the minus 7th. We've got 2 times 10 to the minus 13th. Which one's going to dominate? The larger K. We've got one that's larger by 6 orders of magnitude. And so this reaction is going to dominate. Are both of them going to happen? Yes. But which one's going to dominate? By far, the Ka2 is going to dominate, and we're going to find that H2PO3, when you put it in solution, is slightly acidic. So when you have a possibility of a conflict, you've got an acidic path and a basic path, you have to find those K values that govern those equations and compare them. The larger K value is going to win. If we had found out that Kb1 was 2 times 10 to the minus 3rd, then it would have been larger than the Ka2. And we would have found that this solution is more likely to be basic than it is to be acidic. All right, sorry for the very long video. I hope that we did okay. Thanks.